Case 3.
Case 3. Why?
Because, like you said, the velocity is like all, it's perpendicular to the arm, so all of it is like going into rotating that arm. Isn't where in the other cases, it's not perpendicular to the arm, so it's not gonna change it as fast.
Yeah. So over here, because this point isn't actually accelerating, right? Or the angular velocity of the small link isn't accelerating. We know that we're not worrying about like a length of time of a certain acceleration will result in the greatest acceleration. Because if we're looking at like a car that's moving along, if we said, well, the speed over here is greater than the speed over here, therefore the acceleration here must be the greatest. That's not true, because you'd have a constant acceleration or a decreasing acceleration and still be increasing, right? So we can't just say highest speed equals highest acceleration, done. But because this link doesn't have an angular acceleration, we can use that kind of logic in our head. We can say over here, when it's back this way, moving to up here, the link is changing in its rotation. So right here, the angular rotation is essentially 0 in the link. And all the way down here, it's essentially 0 again. And so in between, it has to reach a maximum. And so when you think, right here is going to, all of the velocity of this is going to be dedicated to turning this. That's going to be going as fast as it possibly can, which means the most acceleration is right here. Okay? And if we think about it, if it's 0 here, and it's large right here. Is it large? Is it positive or negative? When the omega of this link, is this positive or negative right here? Which way is it going to be spinning?
Counterclockwise.
Yeah, so if this side's going down and this is stationary, it's going to be spinning counterclockwise, which is a positive omega. So if we have a zero velocity that goes, a 0 angular acceleration here to a positive angular acceleration here, we need to have a positive angular velocity here. We need to have a positive angular acceleration in the meantime.
Can you say that again?
Because the angular velocity of this link is 0 here, and omega 3 here is positive. If something goes from 0 to positive in velocity, in between it's got to have a positive acceleration. Okay? And so that's the way that we can say, I definitely know, I'm not entirely sure if this magnitude is right, but the sign definitely is. Because I know that this has to be accelerating in the positive direction. Does that help clear things up a little bit in terms of kind of saying, okay, is my sign right? Do I know what direction this is? Take looking at these extremes. Oh yeah, it's got to be positive. Okay, what's up?
What about when it gets to the, like, if you flip one so that the short bar is down, omega 3 will still be 0, right?
Yes.
In that case. So if omega 3 is like peaking at case 3, wouldn't alpha 3 be 0?
If omega 3 is peaking at case 3, would alpha 3 be 0? So we're saying if our acceleration is some sort of continuous line, it's going from, once we pass here, we're probably gonna have a negative acceleration, right?
Yes.
So our acceleration is going to be positive while we're going up top. It's going to be negative while we're going on the bottom.
Yeah, so it's 0, right?
What?
It is 0?
The angular acceleration here, yes, would be 0.
Okay.
Because if you had, let's say that, if this was like really big, and you had some massive links, and they were almost perfectly aligned. As they were almost perfectly aligned, the velocity at this point would be approximately steady, right? If we zoomed into just a little sliver, the velocity is steady in that line, and so the angular velocity would be equal to 0 when it's above our alpha. We would have some sort of a sinusoidal function where this is case 3, this is case 1, and 2 is somewhere in this vicinity. Yes? That makes sense? Okay, so we have our value for alpha 3. Now we need to find ACX and ACY. Okay, so what's our method for finding ACX and ACY?
Create a vector equation that describes its location.
Yeah. So we're going to do, can I raise this? Does anyone need this? Okay, so Jeremiah, what is our loop equation, or our complex equation for the distance to point C?
A EDI theta 2 plus AC EDI theta 3. I think. Might be minus AC.
Is it positive or negative, guys? Should this term be positive or negative?
Positive.
Minus positive.
Why?
Because the angle find out the base of the vector.
Yes, yeah, so the angle theta 3 is defined over here based off the base, and so when we were doing our loop to B, when we got here, we intersected the tip of the vector and then walked to the base to complete our loop. So that meant that this was a negative value. But when we're going the other direction, we start here and we're going out to C to find that distance vector. And so because theta is defined from the base, we know it's a positive value. So we take our derivative and we'll find the velocity at C. This is going to be how many of these values can change with time? Just theta 2 and theta 3 because we don't have any slots. So we know this is going to be a omega 2 I e to the I theta 2 plus a c omega 3 I e to the I theta 3. Then we take our acceleration derivative and we say it is going to be a alpha 2 I e to the I theta 2 minus a omega 2 squared e to the I theta 2 plus a c alpha 3 I e to the I theta 3 minus a c omega 3 squared e to the I theta 3. Then in order to find our normal or our x and y components of this acceleration, what do we do?
Take the real imaginary parts.
Okay. What about looking at normal, tangential, slip, Coriolis? We kind of have two different systems for figuring out the acceleration at a point. Jeremiah, why do you want to go that direction instead?